This is the beginning of chapter 6, which is called The Structure of Atoms. So let's take a look at some of the problems from the back of the book. Okay, so here's our first problem. Consider the colors of this visible spectrum. Which colors of light involve less energy than green light? Which color of light has photons of greater energy, yellow or blue? And which color of light has the higher frequency, green or blue? So we need to know a little bit about electromagnetic radiation. So electromagnetic radiation is a type of radiation that involves an electrical component and a magnetic component. And there are different types of electromagnetic radiation. So I'm going to give you a little chart that shows you the types of electromagnetic radiation. And it's also going to show you the strength of it versus the wavelength. And then I'm going to talk to you about some of the properties of electromagnetic radiation. Actually, let's go with the properties first. So properties of electromagnetic radiation. One is called wavelength. And for the wavelength, we use the symbol lambda. So that looks like an upside down Y. Lambda. And usually we measure this in meters or nanometers. Another property we have is called frequency. Now our book uses something called nu. And other books will use an F for frequency. And frequency is measured in per second. There's also the speed of light. And the speed of light is a lowercase c. And this is going to be given in meters per second, usually. And you should know that the speed of light is a particular value. 2.998 times 10 to the 8th meters per second. So you should commit that value to memory. Now, these three properties are connected together. And they're connected together by the following formula. C equals lambda nu. So if you know the wavelength of the light, you can calculate its frequency. And if you know the frequency, you can calculate its wavelength. Okay. Now, there's something else you want to know about the property of light, and that's the energy. So you can actually calculate the energy of a specific wavelength of light or a specific frequency of light. And energy is equal to h nu. This is Planck's equation. And since nu is equal to c over lambda, this is also equal to hc over lambda. And perhaps E equals hc over lambda is more useful than E equals h nu. Okay, so let's look at the types of electromagnetic radiation. And the types of electromagnetic radiation are gamma rays. So this is the symbol for gamma. That's the symbol for gamma. We have X-rays. We have ultraviolet light. So UV is the symbol for ultraviolet light. And then there is visible light, which is given the symbol VIS for visible. Then there's infrared light. Then there's microwaves. You'd think that we'd use the symbol micro for microwaves, but we don't. And then there are radio waves. And the radio waves are split up into long and short radio waves. Now, when we look at these and we look at the energy of these different types of electromagnetic radiation, energy increases to the left. So this arrow points to more. more energy for an X-ray versus radio waves. Now, for the wavelength, it goes this way. So going to the right, we have longer wavelength. To the left, we have shorter wavelength. Now, this kind of makes sense because we can see that the relationship between energy and wavelength is inversely proportional. So that means as the wavelength increases, the energy decreases. Now, we can also put frequency here because we can see that from this equation, energy and frequency are directly proportional. So X-rays have more energy, they have higher frequency, and they have shorter wavelength. Okay, let's take a look at the visible light in particular. And this is stuff that you should know. So I'm going to make it match this chart right here where we have high energy on the left and low energy on the right. So I'm going to repeat that little chart, and it's going to have gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. Now remember, energy is to the left and wavelength is to the right. So let's look at this visible light and spread it out. So here is basically visible light. So we're going to go in increasing wavelength. So this is going to be 400 nanometers to approximately 700 nanometers. Some people cut this off at 650 nanometers because you don't really see 700 nanometer light. Now, what are the colors associated with each of these? Well, they are going from 400 nanometers to 700 nanometers, VIB, GIOR. V stands for violet. I stands for indigo. B stands for blue. G stands for green. Y stands for yellow. O stands for orange. And R stands for red. Okay, so if you look at this backwards, it's Roy G. Biv. And I make a joke that when we look at the visible light in increasing wavelength, the Russians discovered this. The scientist who discovered it was a gentleman by the name of VIB GIOR. When we look at the visible light in increasing energy, which was discovered by an American scientist, it's Roy G. Biv who discovered it. Okay, nonetheless, you want to know that short wavelength light is violet and long wavelength light is red, and it's VIB GIOR. Okay, so another thing that we can say about light is that there are two models of light. One model is the wave model. So two prevailing models of light. One is the wave model. And here we have wavelength, frequency, speed of light. And the other is the photon model. A photon is a massless packet of energy. Now, it turns out that the equation that we use for the photon model and the wave model are identical. So here we have E equals h nu, And here we have E equals H nu. Now here, the energy is the calculation for the energy of a particular wavelength of light, which when you think about it, seems kind of strange, because what if you have a particular wavelength of light, say green light, and it has a particular amount of energy? How would the calculation differ if you had two green lights? You would double the energy, but how would you know you have two green lights? So this model is a little bit weird. It's just basically the energy of a particular wavelength of light without regard to how many lights you have of that color. The photon model, this energy we're calculating is the energy of one photon. And you can see based on the formula, that energy is going to be a discrete amount. Now, for this equation here, we should know Planck's constant. Now, it's been a long time since I used this, so I'm going to give a shot at it and then look it up. Planck's constant is 6.626 times 10 to the minus 34 joule seconds. That's what I remember it as, but I'm going to double check and make sure it's correct. So this is chapter 6. And this is definitely something you want to put on your index card for your exam. And so double checking Planck's constant. Where is it? .626 times 10 to the minus 24 joule seconds. Now, you might want to note that this is joules times seconds, not joules per second. Okay, and we recognize J as an energy unit and second as a time unit. Okay, so you can see that when we use this equation, E equals H nu, if H is joule seconds and nu is per second, that ends up being joules, which is a perfectly acceptable unit for energy. Okay, so those are some background so that we can do a few of these questions. So consider the colors of the visible spectrum. Which colors of light involve less energy than green light? So if we want to use the energy model, where energy increases to the right, we get to use Roy G. Biv. So remember, this arrow points to greater energy. So what colors of light involve less energy than green light? The answer to A would be Roy. Red, orange, yellow. Which color of light has photons of greater energy, yellow or blue? Well, here we can see that blue has greater energy. And which color has light of higher frequency? So frequency and energy match, because we can see that the greater the frequency, the greater the energy. So which color of light has higher frequency, blue or gray or green? You can see that blue has a higher frequency. So you may want to commit this to memory, that when you're going from increasing energy, it's Roy G. Biv. Roy is low energy, V is high energy. Okay. Let's take a look at our next question here. Suppose you are standing 225 meters from a radio transmitter. What is your distance from the transmitter in terms of wavelength if the station is broadcasting 111.50 kilohertz on the AM radio station, And 1 kilohertz is 1 times 10 to the third hertz, or 8,000 hertz. And the station is broadcasting at 91.1 megahertz on the FM radio station, where 1 megahertz is equal to 1 times 10 to the 6 hertz. Okay, so what is this term hertz? Well, it turns out that a hertz, like the car company, which has the symbol Hz, is equal to 1 per second. So it's just another way to say per second, but instead of saying per second, you say hertz. So we want the distance from the transmitter in terms of the number of wavelengths. Okay, so we're going to try this formula. C is equal to lambda nu. Okay. And we're standing 225 meters from a radio transmitter. So we know that the distance is equal to 225 meters. And we want to know how many wavelengths between you and the radio transmitter. So here's your radio tower, the transmitter. And this is you. And the distance between you and the transmitter is 225 meters. Now, I think what we can do is we can calculate the time it takes for the radio wave to reach you. I think that may be useful. But here, we want to calculate the number of wavelengths. So this is kind of interesting. How do we do this? Well, here I'm going to draw a little imaginary wavelength. So here's the wave coming from the radio station to you. This is 1 wavelength. You can see that the wavelength goes from top to top, or it could go from bottom to bottom. It just goes from one like place to another like place. Okay, so we want to calculate that distance here of wavelengths between you and the person, or the radio station and the person. Okay, so what we need to do is figure out the wavelength of the wave, and that's this right here. So when we figure out the wavelength of the wave, and we do this, the wavelength times the number of wavelengths is going to be equal to the distance. I think that makes sense, right? If you have 1 wavelength, the distance is equal to 1 wavelength. If you have 2 wavelengths times this, the distance will be double. So this is the number of wavelengths. So that means that this number of wavelengths, I'm going to write this as this, times n is equal to the distance. Then the number is equal to the distance divided by the wavelength. So we already know that the distance is 225 meters. We just need to know the wavelength. So here's how we calculate the wavelength. Wavelength is equal to C over nu, which is 2.998 times 10 to the 8th meters per second. All of this over the frequency, which we have as 1,150 times 10 to the 3 per second. So remember, a hertz is a per second, so I just substituted that. So I'm going to take my calculator out and try and solve this. These seconds that are both in the denominators cancel, so the wavelength is here going to be ending up being in meters. This is 1.15 times 10 to the third times 10 to the third, which is 1.15 times 10 to the 6. 1.15 will go into that about 2.5 times maybe, and then times 10 to the squared is what we should get. So let me see what we get here. 2.998 second EE8 divided by 1150 second EE3 is equal to. So we get 200, and we get 3 significant figures because of that 1150. 261 meters. And now we get to use this formula over here where n is equal to the distance divided by the wavelength, which is 225 meters divided by 261 meters. And we can see the answer is going to be a little less than one wavelength. And I get 0.863 wavelengths. So not even one wavelength between the radio tower and you. So this is a bad drawing. Okay, so that's A. The station is broadcasting at 1,150 kilohertz. So what about B? Well, for B, we can use the same information, only we have 98.1 kilohertz. So all of this was for A. For B, we can kind of speed it up a bit. That is to say, we can calculate the wavelength is 2.998 times 10 to the 8th meters per second, all over 98.1 times 10 to the 6 per seconds. When we calculate that, let's see what we get. We're going to get a number that's smaller than this because it's a bigger number on the bottom. And indeed, I do get a smaller number. I get 3.06. And that's meters. So what do we get for the number of wavelengths? That's going to be 225 meters divided by 3.06 meters. Okay, 225 divided by 3.06, and we get 73.5 wavelengths. So if we look at the A versus B, if this is the tower and this is the person, we have not quite one wavelength between the tower and the person, so it would look kind of like this. So you see, we don't get back to 0 here, and this would be for A. And for B, it would look more like this. And there's 73.5 wavelengths in there. Okay. All right. So let's put that off to the side. Okay, 6. Violet white light has a wavelength of about 410 nanometers. What is its frequency? Calculate the energy of 1 photon of violet light. What is the energy of 1 mole of violet photons? And compare the energy of photons of violet light with those of red light. Which is more energetic? Okay, so let me get a fresh piece of paper here. Okay, so we have the wavelength is equal to 410 nanometers, which is 410 times 10 to the minus 9 meters. We can substitute 10 to the minus 9 for nanometers because that's what nano stands for. Okay, so we want to calculate the frequency. So we're going to go ahead and use C equals lambda nu. So nu is equal to C over lambda, which is 2.998 times 10 to the 8th meters per second, all over 410 times 10 to the minus 9 meters. So we're going to be left with units of per second. You can see that this 10 to the minus 9 and this 10 to the 8 are going to add up to 10 to the 17. And 410 goes into 2.998, something like a 0.008 times or something like that, or 7 times. And so we'll end up getting like a 7 times 10 to the 15. Okay, 2.998 second EE8 divided by 410 second EE negative 9. And we get 7.3 times 10 to the 14. So I think I said 15, so I was a little off. And now I know why. But at any rate, this is the new, and so that's going to be per second. So this is the answer to what is the frequency. So I'm going to call that A. So B is calculate the energy of one photon. So here we get to use A equals H nu. So we get 6.626 times 10 to the minus 34 joule seconds. And the frequency is 7.3 times 10 to the 14 per second. And here we can see that if we put this over 1, it's really easy to see that the seconds cancel. And when we multiply these, you can see that 6.6 times 7 is going to be like 50. And negative 34 times 10 to the 14 is going to be like negative 20. So we're going to have like 50 or 5 times 10 to the negative 19, I think. So 6.626 second EE, negative 34, times 7.3 second EE 14. And we get 4.8 times 10 to the minus 19. Oop, that's supposed to be a 9. And that would be joules. Okay. Part C. What is the energy of 1 mole of violet photons? Well, this is the energy per 1 photon. So 1 mole is going to be the energy of 1 times 6.022 times 10 to the 23rd. And that would be photons, or mole, actually. So this is the energy of, I'm going to say this is the 4.8 times 10 to the minus 19 joules per 1 photon. So for the energy of 1 mole, we're going to say 1 mole of photons times, and I'm going to go ahead and use a conversion factor here, 6.022 times 10 to the 23rd photons per 1 mole of photons, and then times 4.8 times 10 to the minus 19 joules per 1 photon. Okay, so you can see that this number is going to be pretty large. So I get 3.2 times 10 to the 5. Let's see, mole photon, photon, joules. Okay, so that's C. Compare the energy of photons of violet light with those of red light, which is more energetic? Well, all we have to do is draw our little energy here in Roy G. Biv, and we can answer that question. We don't need to do any calculations. So remember, the question here is compare the energy with violet with those of red, which is more energetic. So we're looking at violet and red, and we're going to say violet photons are more energetic. So that means if you get hit with a violet photon, it could cause more damage than a red photon. Okay, so there's that problem. All right, number 8. The most prominent line in the emission spectrum of magnesium is 285.2 nanometers. Other lines are found at 383.8 nanometers, and 518.4 nanometers. In what region of the electromagnetic spectrum are these lines found? Which one is the most energetic? What is the energy of 1 mole of photons with wavelength of the most energetic light? Okay, so this comes from the idea of the uh, uh, structure of the atom. So we don't really need to know the structure of the atom to be able to do this, but let's go ahead and introduce the idea that we will be learning about the structure of the atom. So what is an emission spectrum? An emission spectrum is when you take a metal such as magnesium and you heat it up to red hot like a piece of iron, it will emit electromagnetic radiation. And when you pass that radiation through a prism, you can actually see the different wavelengths that are emitted. Now, you might think, okay, so if we do that with magnesium, we're going to see that the spectrum is going to look kind of like putting light through a prism. We're going to see a rainbow of colors. And surprisingly, you don't see a rainbow of colors. What you see are distinct wavelengths of light. So you see wavelengths of light, boom, boom, boom. And here it looks like we see a 285, a 383, and a 519 lines in the emission spectrum. There are more lines than that. So you see these lines of spectrum instead of a rainbow of colors. And that's what happens when you heat up any sample of a particular element. You get what's called a line spectrum. And the line spectrum is as good as a fingerprint. It's better than a fingerprint for identifying the type of element that is emitting that particular spectrum. In fact, that's how we know what different stars are made out of, is we take their spectrum and we analyze it for the different elements that are in that particular star. It's a little more complicated than that because it's a very complex spectrum, but you start teasing out, well, this wavelength is this wavelength is this wavelength is this. And you have to have some very fine instruments to be able to do this. And it's taxing, it takes some time, but with computers, it just makes things a whole lot easier. Okay, so we have 285 nanometers, so 285.2, 383.8, and 518.4. So this is an increasing wavelength, which means that the energy is actually going in the opposite direction. So that means we're looking at Vib Gyor, not Roy G. Biv. Okay. All right. In what region of the electromagnetic spectrum are these wavelengths found? So here, these, I would say that this one is in the visible, 518, because remember, visible is basically 400 nanometers to about 700 nanometers. So here, these two are to the left of visible light, and it goes gamma, X, UV, vis, IR, microwaves. Let's see, here's the symbol for microwave, and then radio. So here we're looking at, these are ultraviolet. So the answer to A is going to be 285.2 nanometers and 383.8 nanometers are ultraviolet. 518.4 nanometers is visible. And what is the energy of 1 mole of photons with the wavelength of the most energetic light? Okay, so the most energetic is 285.2 nanometers. So the energy is going to be H nu, which is H C over lambda. So we can do this, 6.626 times 10 to the minus 34 joules per second for H, 2.998 times 10 to the 8th meters per second for the speed of light. Oops, and I made a mistake. This is joules seconds, not joules per second. And the wavelength is 285.2 times 10 to the minus 9 meters. Okay, so the meters cancel, the seconds cancel, and we'll be left with joules. So that's the energy of one photon. One photon. So what do we need to do with this number? We're going to have to multiply by 6.022 times 10 to the 23rd. So let's see what we get. 6.626 second EE negative 34 times 2.998 second EE 8, and then divided by 285.2 second EE negative 9. So here I'm going to get four significant figures, 6.71196 times 10 to the minus 19 joules. So the energy of 1 mole is going to be 6.022 times 10 to the 23rd photons, because that's 1 mole, times 6.71196 times 10 to the minus 19 joules per 1 photon. And let's see what we get. You can see that we're going to get like 10 to the 4 some sort, or maybe 10 to the 5. And we get 4.042 times 10 to the 5 joules. So that's the energy of 1 mole of photons with the wavelength of the most energetic light. So something to remember: short wavelength, high energy. Okay, place the following types of radiation in order of increasing energy per photon. So for this, we just need to know that little chart: gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. So radiation within a microwave oven, so that's A. Your favorite radio station, so that's B. Gamma rays from a nuclear reaction, so that's C. Red light from a neon sign, that's D. And ultraviolet radiation from a lamp. Okay, so in order of increasing energy per photon. Now this is actually backwards. So if we want to put them in increasing energy, we start at the low energy, which is B, is lower in energy than A, which is lower energy than D, lower energy than E, and lower energy than C. So this is energy. And there's your answer. Let me see how many more of these we want to do. Okay, we're going to do a couple of more, and then we're going to hold off because we're going to start getting into the structure of atoms and emission spectrum and absorption spectra. Okay, you are an engineer designing a switch that works by the photoelectric effect. The metal you wish to use in your device requires 6.7 times 10 to the minus 9 joules per atom to remove an electron. Will the switch work if the light falling on the metal has a wavelength of 540 nanometers or greater? Why or why not? So the photoelectric effect basically works as following. This is a photo diode, if you will. And what happens is light, and here, this is supposed to be a photon. So this is a little misleading because we have a photon with a wavelength and we're kind of mixing the models together. What we should really draw is just a photon. So here's your photon traveling to your photodiode, or your photocell is what the book calls it. And it's going to hit a metal, a piece of metal. So this is the metal. And when it hits the metal, what's going to happen is an electron gets knocked off the metal and travels to the anode. Now, the anode is called the anode because it attracts the electron, which is kind of like an anion. Okay, so your electron goes through there, and it goes through a little measuring device, and it comes back here to the metal, which is also your cathode. Okay, so here, this electron that travels through the wire is electrical current. And when you are hitting the metal with enough energy and knocking electrons off, you're creating an electrical current which can run something. It can run a device, like maybe open a door or shut a door. Okay, so this is a switch that works by the photoelectric effect, and it will work as long as photons of a particular wavelength of light are hitting your photocell. Okay, so you can create an electrical current. Okay, so it requires 6.7 times 10 to the minus 19 joules per atom. So what is this joules per atom? That's telling you that's how much energy your photon must have, because one photon can knock off one electron. That's kind of the rule of thumb. One photon, one electron. That's it. Okay, so we can think of this as being joules per one photon. So for this 6.6, we can use the energy of one photon is equal to h nu, and that's going to be 6.7 times 10 to the minus 19 joules, because 6.7 times 10 to the minus 19 joules per atom is equal to 6.7 times 10 to the minus 19 joules per photon. And since we know this is the calculation for one photon, we can actually say that this is the energy. Now, what we're going to do here is we're going to calculate the frequency of light needed to generate this much energy. So we're going to say the frequency is 6.7 times 10 to the minus 19 joules per energy. Okay. Now, notice this says we're actually looking for the wavelength, so we can just take a pause here and change this. So instead of using this formula, we can use E equals hc over lambda. And this comes to the wavelength is equal to hc over the energy. And so this is going to be the wavelength needed to generate that much energy. So the wavelength is going to be 6.626 times 10 to the minus 34 joule seconds. C is 2.998 times 10 to the 8th meters per second. And the energy we need is 6.7 times 10 to the minus 19 joules. Okay, so let's see what wavelength will generate that much energy. And remember, they asked you for here, is 500 nanometers or greater going to give us that energy? We're going to do this another way in just a moment. So here, let's do the calculation. 6.626 second EE negative 34 times 2.998 second EE8, and then divided by 6.7 second EE negative 19. So my estimate for this should be negative 19 and goes to the top is positive 19. Positive 19 and 8 is 27. 27 and negative 34 is negative 7. So I should get somewhere along the lines of 20 times 10 to the minus 7, or 2 times 10 to the minus 6. Did I do that right? Oh, I forgot to divide by my 6. So it's going to be more like 3 times 10 to the minus 7, something like that. And we get 3.0 times 10 to the minus 7 meters. Now, we need nanometers because we're going to compare this to 540 nanometers. So I'm going to multiply by 1 nanometer Actually, I'm going to take this and rewrite it. And I'm going to put 3.0 times 10 to the minus 7 meters times 1 nanometer over 1 times 10 to the minus 9 meters. And I get 296 nanometers. So how do I use this answer compared to 540 nanometers? Okay, so here, remember, wavelength tells you kind of the opposite about energy. Shorter wavelength, higher energy. So this is higher energy, and this is lower energy. Because if we look at that electromagnetic spectrum, and we go energy going this way, actually, I like doing it the other way, and wavelength going this way, we've got gamma, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. So when you start increasing the wavelength, you get less energy. So here, this is a higher wavelength, so it's less energy than this. So yeah, that should be enough energy to turn your photocell on. So what's another way to try and do this one? Well, let me show you. So what we're going to do here instead is we're going to calculate the energy provided by 504 nanometers and see if that energy is enough to turn on the light. So it's got to be 6.7 times 10 to the minus 19 joules or greater. So here we get E equals H nu, which is equal to HC over lambda. So here we can actually plug these numbers in. We get 6.626 times 10 to the minus 34 joule seconds. 2.998 times 10 to the 8th meters per second. All of this divided by 540 times 10 to the minus 9 meters. So let's calculate this energy. 6.626. I should just memorize this product, but I don't. Times 2.998. So 1.98 times 10 to the minus 25 on top, divided by 540, negative 9. And we get 3.6, actually 3.7 times 10 to the minus 19 joules. So for this 540 nanometer light, each photon has 3.7 times 10 to the minus 19 joules. Did I do that right? Let me make sure I plug my numbers in correctly. 6.626, because I think we're getting the opposite answer. Or maybe I interpreted the information incorrectly before. 6.626 second EE negative 34 times 2.998 second EE 8 divided by 540 second EE negative 9. So yeah, so for this energy provided by 540 nanometer light is 3.7 times 10 to the minus 19 joules, which is less than that required. So it does not work if I've done my job correctly here. So let's take a look at the previous answer that we got. Now, in this case, what we're doing is we're calculating the wavelength needed to generate this light. And we found out that this is the wavelength needed to generate this light, 296. And so here we're asking, if the light has a wavelength of 540 nanometers or greater, why? Well, here this is what we need. And this is, or excuse me, this is what we need. And, oh, I see what I'm doing. I'm interpreting wrong. This is what we need. This is what we have. So there's not enough energy. Not enough energy. To operate the photocell. So it's actually a misinterpretation on my part. I was mixing up the need with the have. So again, this is what we need to operate the photocell, this amount of wavelength or shorter. This is what we have, and this is too short to operate that photocell. Okay. And I think we're going to do one more. The most prominent line in the spectrum of neon is found at 865.438 nanometers. Other lines are located at 837.761 nanometers, 878.062 nanometers, 878.375 nanometers, and 885.387 nanometers. In what region of the electromagnetic spectrum are these lines found? So again, this is the way I like to do it. Energy this way and wavelength this way. We've got gamma rays, X-rays, visible rays. Oops, excuse me. That should be UV, visible, infrared, microwaves, and radio waves. Okay, we know that UV, or visible, is 400 to 700 nanometers. So here, we know that anything shorter than 400 nanometers is ultraviolet. Anything longer is probably going to be infrared. So these are pretty close to 700 nanometers. So we're going to say A is going to be infrared. Now, the questions that the book asks you don't really rely on you knowing more wavelengths than the visible wavelengths. So if anything's going to be around, you know, say, I don't know, up to say 3,000 nanometers, you're going to say infrared. And for ultraviolet, if it goes down into like a 1 meter, you're going to say ultraviolet. Okay. Are any of these lines found in the spectrum of neon shown in figure 6.6? And the answer is no, because the figure only shows visible lines. So let's take a look at that 6.6 figure. And that's my guess, is it only shows visible lines. So chapter 6, figure 6.6. And here's figure 6.6. Here's neon, and you'll notice these are all visible lines, so none of these are being shown. And that goes from 400 to about 700 nanometers. Okay, so are any of these lines found in the spectrum of neon? No, because the figure only shows visible lines. C, which of these lines represents the most energetic radiation? Well, remember, short wavelength is more energetic. So we're going to look at all of these lines and find out which one is the shortest. Looks like the 837.761 nanometers is the most energetic. Okay. What is the frequency of the most prominent line? So here we have to read carefully and see that the most prominent line is 865.438. Not the most energetic, the most prominent. So that's one that you see the best. So we've got the wavelength is 865.438 nanometers, and we're asked for the frequency. So what we're going to do is we're going to do C is equal to lambda nu. So nu is equal to C over lambda, which is 2.998 times 10 to the 8th meters per second, all over the wavelength, which is 865.438 times 10 to the minus 9 meters. And so we're going to get a value that's going to be somewhere like 10 to the 17, but then it's going to be changed by this. So it'll probably be like 10 to the, I don't know, 14 or 15. Let's see what we get. 2.998 second EE 8 divided by 865.438 second EE negative 9. And we get 3.04 significant figures, 464 times 10 to the 14 and per second. So that's your frequency. Okay, so that's our first little doodad on problems for Chapter 6, Structure of the Atom. Thank you for listening.